Hi everyone, welcome to goclasses. In this lecture, we will study intermediate representation optimization, intermediate code optimization. So this is the first lecture for optimization, IR optimization. So let me tell you, in the compilation process, now we are here. We have already seen intermediate representations. We have seen three address code, quadruple representation, triple representation, indirect triple, control flow graph, SSA, static single assignment. So basically, these are the most important intermediate representations that we have already seen. Okay, we have already studied. We have already seen what is control flow graph, basic blocks. Okay, so all these concepts we have seen. Now we are here. Intermediate representation optimization. The intermediate code that will be generated from intermediate code generator, the intermediate code that we will get, we want to optimize it. Okay, so this is our lecture, intermediate representation optimization. Let me tell you, you already know that this intermediate representation, this is a platform independent, machine independent, also source language independent. So this optimization that we perform on the intermediate representation, this is basically machine independent optimization. Okay, so this is platform independent optimization. Independent optimization means the optimization that we will discuss, that will not depend on the machine, that will not depend on the specific platform or specific CPU. Okay, so basically this IR optimization, this is the optimization that we perform on the intermediate code. Intermediate code is platform independent, so this optimization, this is also machine independent optimization. Okay, so you can see in the compilation process, this is the complete compilation process. Initially we have the source code, or I can say character stream. Our source code, that is a stream of character, sequence of characters. So first we have lexical analyzer. In the compilation process, the first phase of compiler, that is a lexical analyzer, it will convert our character stream to token stream. Okay, and then syntax analyzer, it will convert our token stream to syntax tree. Then semantic analyzer, which will do the semantic analysis. Okay, so the output of semantic analyzer, that will be annotated syntax tree. Then we have intermediate code generator, it will generate the intermediate representation. This intermediate representation, this is source language independent, also machine independent. Okay, on this intermediate representation we perform the optimization. Okay, so you can see, because this intermediate representation is platform independent, machine independent, so the optimization that we perform, that is also machine independent optimization. So the output will be optimized intermediate representation. Okay, and from the optimized intermediate representation we can generate the target machine code. So there is a code generator which will generate the target machine code, and this target machine code, this also we can optimize. So basically this will be machine dependent optimization. In the gate syllabus we only have machine independent optimization, means we only have IR optimization. Okay, in our gate syllabus we have intermediate code optimization, means machine independent optimization. Okay, so you can see this machine independent optimization, this is what we have in the gate syllabus. Okay, let me tell you one thing, that among all the phases of the compiler, this intermediate representation optimization, this is the most complex phase. Let me tell you. Okay, if you see all the phases individually, lexical analysis phase, syntax analysis, and so on, then let me tell you, this intermediate code optimization, this is the most complex phase. This is the most complex phase of compilation process of compiler. Okay, also let me tell you that this optimization, IR optimization, this is a very active area of research. This is still very active area of research. For example, when you go to IIT for MTech, if you go to a top college, then in almost all the colleges, in almost all the top colleges, you will find a course on optimization or on program analysis. Okay, so basically these courses you will find, like program analysis course, static analysis, dynamic analysis, or you will find some course on intermediate representation optimization. So basically this optimization, remember, this is a very active area of research. For example, when you go to a top college, you will not find a course on lexical analysis. Okay, you will not find a course on syntax analysis, but definitely you will find some course which will be related to optimization, IR optimization. So remember, this is a very active area of research. Okay, and this is the most complex phase. But good thing for us that we don't have to worry about this complex phase. Okay, because in our gate syllabus, or I can say in our in the undergrad when under in a undergraduate course, basically, okay, in a btech course or undergraduate course, basically we just have to study some specific analysis. Okay, some specific optimizations we have to study. We do not have to worry about all the type of optimizations. Okay, in our syllabus there are some specific optimizations, those we need to study, that's it. Okay, so let's see what is IR optimization. The name itself is telling you optimization means we want to optimize the code. Optimize means improve. So basically we want to improve our intermediate code. So remember, by IR optimization, IR means intermediate representation, or I can say intermediate code. So by IR optimization we mean IR improvement. Okay, so when we say optimization, remember, then we are talking about improvement only. Okay, now, so improvement in terms of what? We want to improve our intermediate code, but improvement in terms of what? Which properties or which quantities we want to improve? So the answer is very simple. We want to improve the execution time. We want to improve the space requirement, means we want to reduce the amount of memory that is needed. And when I say we want to improve execution time, it means that we want to take less execution time, or I can say we want to increase the execution speed. Okay, so the time taken should be less, the space taken should be less, and the power consumption should be less. Okay, so these are the main parameters that we want to improve. Okay, so when I say optimization, then basically these are the parameters that we want to improve. And of course there are some more parameters. For example, we want to minimize the function calls, we want to reduce the use of floating point hardware in our computer system. In our ALU, arithmetic logical unit, in that ALU there is a hardware, floating point hardware. So we want to reduce the use of floating point hardware. Okay, this reduce the use of floating point hardware, basically that we do for lower power consumption. Okay, so overall the point is very simple. What is this optimization? The definition of optimization is very simple. The name itself is telling you optimization means improvement. Okay, we want to make our intermediate code smaller, faster, cheaper. When I say cheaper, means lower power consumption. Okay, so these are the parameters that we want to improve. Very simple. Now let me tell you that when I say improvement, then definitely there is some transformation involved. Yes or no? We have an intermediate representation. That intermediate representation we want to improve, we want to optimize. Okay, optimization means improvement. So when we improve our intermediate representation, then basically we are transforming our intermediate code to some other form. Yes or no? That is what we mean by improvement. So we have our code, we want to make it smaller so that it will take less memory. Okay, less space it will need. Okay, and we want to increase the speed, execution speed. So basically it should take less execution time and less power consumption. So basically you can see that in the optimization, remember, there is transformation involved, means we want to transform our intermediate code to a optimized intermediate code. Okay, so you can see the optimization is basically transformation, code transformation, you can see. And one more thing, this is important, that the optimization, or I can say this transformation, basically this must be safe. What is the meaning of safe? Safe means semantics preserving, or I can say function preserving. So the optimization, or I can say the transformation, that must be safe. Safe means that it should not change the meaning of the program. Okay, your transformation, your optimization should not change the semantics of the program. Semantics means meaning of the program. Yes or no? This is the meaning of semantics. Whenever you see this word semantics, it means meaning of the program. So basically our optimization should not change the meaning of the program, it should not affect the behavior of the program. Okay, this is the overall point. With example this point will become very clear, but overall the point is very simple, that optimization is basically code transformation, and this must be safe. Safe means semantics preserving. Okay, means it should not change, it shouldn't change the meaning of the program, it shouldn't change the observable behavior of the program. Okay, it should never change the behavior of the program. Very simple. So you can see that optimization must be semantics preserving, means the meaning of the program should not change. Okay, you can see it does not alter, it does not change the semantics, or I can say meaning of the original program. Okay, and remember, all the optimizations that we will study, they are semantics preserving. Okay, means all the optimizations that we will study, they will not change the meaning of the program. And this is the property of any optimization. If you are performing some optimization on a intermediate code, then it must be semantics preserving. Okay, it must not change the meaning of the program, the behavior of the program. Let's see some examples. Consider this example. We have this original intermediate code, and we are transforming this code to this code. So this transformation we are doing, tell me, is this optimization, or I can say, is this transformation correct, safe? Is this safe transformation? Is the following optimization or transformation correct or safe? Safe means semantics preserving. Tell me, is this optimization correct? You can easily see in the C language, here we have main function, here we have function f. Okay, and if you remember, in the C program, this main function, this is the starting point of the execution. When we execute a C program, then the execution will start from the main function. Okay, this main function will be executed first, and you can see this main function, this is not calling this function f. Yes or no? We will start the execution from the main function. In the main function, we are just returning 42, and you can see we are not calling this function f. This function f we are not calling at all. So you can see this code, if I transform and if I make this code, if I convert this code, this left code to right code, then this is a correct transformation. Yes or no? Because anyway, you can see that this main function is not calling this function f. This function f is unreachable, I can say, from the main function, because this is the starting point of the execution. So from the main function, this function f is unreachable. We will never reach this function f. So definitely I can remove it. This is what it means by optimization. Okay, you can see we are not changing the meaning of the program, we are not changing the semantics, we are not changing the behavior of the program, because the program execution will start from the main function, and the main function is not calling the function f. So this function f is unreachable, we can remove it. So the answer is very simple: yes, this transformation is safe, or I can say this transformation is correct. Let me tell you, this optimization is called unreachable procedure elimination. You can see this function f, this is a procedure. This main function, this is also a procedure. So in this program, we have two procedure, two functions, main function, f function. But you can see that from the main function, which is the starting point of the execution, from this main function, this function f is unreachable. So this optimization, where we are removing the unreachable procedure, unreachable function, this optimization is called unreachable procedure elimination. So this is the name of the optimization. Okay, is this point clear? Very simple. Let's consider this example. Is this optimization, is this transformation safe, correct? Is it semantics preserving? Tell me. Look at this transformation. Is it safe? Is it correct? Here you can notice we have this main function which is calling function f, and you can see we are removing function f here. Can we do that? No, we cannot do that. Yes or no? You can see from the main function we are calling function f. So definitely this function f is reachable. Okay. So you can see on the right side we are removing function f. So definitely that is wrong. We are changing the behavior, we are changing the semantics. The whole meaning of the program has changed. Okay. This was a good program, but here you can see this is nonsense. There will be error. You are calling function f, but there is no function f here. Yes or no? So very simple. Remember, this transformation is not correct. You can see. I hope you understood this point. Very simple. Let's consider this example. Is this transformation safe, correct? Let me know. On the left side, we have a program, we have a code which we are transforming to the code on the right side. Now tell me, this transformation, is it safe? Is it correct? You can notice that what changes we are doing. Just notice the changes here. You can see that this k into 2, we are multiplying k with 2, and on the right side, this we have, this we are shifting outside the loop. Here you can see that in the while loop, this k we are multiplying with 2, But you can see on the right side, this k multiplied by 2, this we are shifting outside the loop. Okay, tell me, can we do that? This k multiplied by 2, can we shift it outside the loop? You can notice that in this loop, if this loop is running, let's assume 1000 times, then also you can notice this variable k is not changing. Yes or no? Variable j is changing, variable I is changing, but this variable k is not changing. So let's assume initially the value of k was, let's assume 50. Then here the value of k, this k into 2, this will become 100. And you can notice that whatever iteration we do, even if we have, let's assume 1000 iterations, if this loop runs 1000 times, then also in every iteration here you can notice we will multiply k with 2. In every iteration there will be unnecessary multiplication, because remember, the result of this operation, the result of this expression is not changing in any iteration. The variable k is not changing when this loop is running. So definitely, if you are running this loop 1000 times, then unnecessary you are multiplying k with 2 in every iteration. 1000 times this multiplication you are doing, which is unnecessary. What you can do, you can do this multiplication outside, store the result in some variable t, and that t variable you can use in the loop. Now you can notice when this loop will run 1000 times, then every time in every iteration you are not doing this multiplication. Okay, so you will save a lot of time. Agree? So here we are saving a lot of time by doing this. So definitely yes, this transformation is correct. Did you understand? So remember, this transformation is correct, and let me tell you, this optimization is called code motion. Okay, because we are moving the code from this loop, we are moving this code outside. The reason is simple, because this, the result of this expression is not changing when this loop is running. Okay, look at this expression, the result of this expression is not changing when this loop is running. So I can shift it outside the loop, so that if this loop is running 1000 times, then this expression will not be computed 1000 times. I can just compute this expression only one time, and then that result I can use in this loop. Okay, so a lot of time we will be saving, I can say. So this is called code motion. This optimization is called code motion. I hope you understood. Let's consider this example. Tell me, this transformation, this optimization, is it safe? Is it correct transformation? Think about it. You can notice the same thing we are doing as in the previous example. This k multiplied by 2, this we are shifting outside the loop. Can we do that? No, we cannot do that, because when this loop is running, this value of k is changing. So remember, the result of this expression is changing by every iteration. In every iteration, the result of this expression is changing. So we cannot shift this outside the loop. Okay, is this clear? So remember, this transformation is wrong. I hope you understood the reason, because you can notice that here the variable k is changing. So the result of this expression is also changing. Okay, when this loop is running, in every iteration the result of this expression is actually changing. So remember, you cannot shift it outside. We cannot do that. I hope you understood this point. Very simple. So this optimization is wrong. We cannot do this type of transformation. We cannot call it optimization, because this is wrong transformation. I hope you understood. Now let's see next point. Let me tell you, optimization means analysis plus transformation. And this is a very important point. As we move on this point, you will see this is really very important. When we study a specific type of optimizations, then this point will become very important. So remember, optimization means analysis plus transformation. Before doing transformation, we need to analyze the program. It's a common sense. You can think about it. If you are transforming your program from one form to another, okay, you are doing the transformation of the intermediate code, then remember, first we need to do the analysis of the program. Otherwise, maybe your transformation will be wrong, maybe your transformation will not be safe. So very simple point, that optimizations, they require some program analysis to determine if the transformation really is safe or not. Okay, so remember, before doing the transformation, first we need to do some program analysis. Then we need to determine whether the transformation is safe or not. If transformation is safe, then we will do it. Okay, so you can see, in order to optimize a program, the compiler has to be able to reason about the properties of the program. This is called analysis of the program. So before we do the optimization of the program, or I can say before we do the transformation of the program, first we need to do the analysis of the program. Okay, so remember, optimization involves two things. First analysis, first do analysis of the program, then do the transformation. Okay, if you do the analysis, then you will determine whether the transformation is safe or not. If the transformation is safe, then do the transformation. Let me give you analogy to understand this point. I told you that in the optimization there are two things involved: analysis and transformation. Okay, you can see from this example, from this analogy, you can understand. Here you can see the analogy of road construction or highway construction. So tell me, will you directly construct the road without doing any kind of analysis? Will you do that? No. First, what we do before constructing the highway or road, you can see first the civil engineers. Okay, what they will do? They will do the analysis. Yes or no? They will do the analysis. So remember, first they will do the analysis, and once the analysis is done, then they will figure out what is safe transformation. Okay, what is the correct way of building the road. Then finally, after the analysis, this transformation will take place. Okay, yes or no? So remember, optimization simply means analysis plus transformation. There are two things involved in any optimization. In most of the optimizations, there are two things involved. First, we will do analysis of the program. We will find out the information about the program, some properties we will figure out, and then we will figure out whether the transformation is safe or not. Okay, so after the analysis, we will do the transformation. I hope you understood from this analogy that whenever we do the highway construction, then first the civil engineers, they will do the analysis first, and then the construction will happen. Okay, very simple. So remember, optimization means first do analysis of the program, then do the transformation. You can read this here, that most optimizations are only possible after doing some analysis of the program's behavior. Okay, so first we will do the analysis, then we will do the transformation, or I can say first we will do the program analysis, then we will perform the optimization. Let me tell you, these are the analysis that we have in the gate syllabus. So on your screen, I have written, on one side I have written the analysis, on the other side I have written the actual optimization or the actual transformation. Okay, so you can see that these are the analysis that we need to study. These are in the gate syllabus, these we will study. So you can see we have liveness analysis. Remember, this is analysis, this is not the transformation. We are just doing the analysis of the source program. Okay, in the source program, some liveness analysis we are doing. Basically, we are figuring out in this program at any statement which variables are live, which variables are dead. Okay, when we study this liveness analysis, then it will become very clear what do I mean by live variable, dead variable. Okay, but the point is that this analysis we perform, liveness analysis we perform on the program, and we figure out some properties about the program, some information about the program we figure out. Okay, that information is basically which variables are live, which variables are dead at every point. Okay, then you can see that once this analysis is done, you can actually perform two optimizations after this analysis. After doing liveness analysis, we can perform these two optimizations: dead code elimination and register allocation. So you can see that this liveness analysis, it will enable us to perform these two optimizations or these two transformations: dead code elimination and register allocation. Okay, both of them we will study, both are in the gate syllabus. So you can see we will study this dead code elimination, we will also study register allocation. Next, you can see there is another analysis. That analysis is basically available expression analysis. In this available expression analysis, we do the analysis of which expressions are available at any point, at any statement in the program, at any point, which expressions are available. Once this analysis we have done, then we can perform these optimizations: common sub expression elimination and copy propagation. So remember, to perform these optimizations, or to perform these transformations, first we need to perform this analysis, that is available expression analysis. Okay. And there is another analysis, that is constant propagation analysis. With this analysis we can perform this optimization, that is constant propagation. I hope you understood this point. The point is very simple, that optimization has two things: analysis and transformation. Before performing the transformation, before performing the optimization, first we will do the analysis. There are different types of analysis: liveness analysis, available expression analysis, constant propagation analysis. These are different type of analysis, and depending on which analysis we have done, different type of optimizations we can perform. Okay. To perform these optimizations, common sub expression, elimination, and copy propagation, to perform these optimizations we need to do available expression analysis. I hope you understood. Let's see one more point, that is analysis direction. In which direction do we perform the analysis? Let me tell you, different analysis we can perform in different directions. For example, when we perform the liveness analysis, this we perform in the reverse direction. Means we do not go in the forward direction, we go in the opposite direction. Okay. And when we perform available expression analysis or constant propagation analysis, then we go in the forward direction. So remember, this analysis, liveness analysis, is done in the reverse direction or in the opposite direction. And this available expression analysis and constant propagation analysis, these two analyses are done in the forward direction. Okay, so you can notice that this available expression analysis, this is done in the forward direction, and this liveness analysis, this is done in the backward direction or opposite direction or reverse direction. So here you can see that this liveness analysis, when we study these analysis, when we study, it will become very clear. But right now you remember that different analysis have different directions. Okay. So for example, this liveness analysis, this is done in the backward direction, or I can say opposite or reverse direction, reverse or backward direction. And these two analysis, available expression and constant propagation analysis, these are done in the forward direction. You will see, when we study these, you will see that these are done in the forward direction, and this liveness analysis, this is done in the backward direction or reverse direction. Now let's study a compiler design terminology, that is def and use. For a variable, when can we say a variable is used and when can we say a variable is defined? So basically def means define, definition, and use means reading. We are reading a variable, we are using a variable. Okay. So let me tell you, this is the terminology that we use when we study intermediate representations or when we study the optimization. Basically, when we study compiler design techniques, then remember, these are the terminology that we use. Whenever there is assignment to a variable, whenever we are assigning something to a variable, then remember, this assignment is also called definition. So when I say that some variable we are assigning, for example, consider this statement z equal to x plus y. So here you can notice that this x plus y, this we are assigning to variable z. So please understand, here variable z is assigned. We are doing assignment of variable z. This we also call that we are defining the variable z. In short, we call it def, or you can say that we are writing the variable z. Okay, so please understand, all these things are same: assignment, definition, def, write. All these things are same. And you can see in this statement, we are using the variable x comma y, or I can say we are reading the variable x comma y, or I can say we are referring to the variable x comma y. So remember, read operation is same as use, that is same as reference, that is same as read, or in short you can call it ref. Reference short becomes ref, or you can call it use. For example, consider this statement. This is the statement n, or I can say this is the, in the program, this is the point n. You can call it point, or you can call it statement n. So let me tell you that for this statement, tell me which variables are we defining. Like for this statement, what is the def of this statement? Means in this statement, which variables we are defining. Definition means assignment. So tell me which variables we are defining? Only variable z we are defining. In this statement, which variables we are using? Use of n, or I can say reference of n, means in this statement which variables we are referring, which variables we are reading. So that is x comma y. Okay, so remember, for this statement, the def comma n, def n means at this statement n which variables we are defining or we are assigning. And when I say use n, it means at this statement n which variables we are using or which variables we are referring or which variables we are reading. I hope this point has become clear. One more thing, remember, here don't confuse with the C language. In the C language, what we say that any variable is defined only once. Yes or no? You cannot define a variable more than once. But remember, in our intermediate representation terminology or in the compiler design terminology, when we study intermediate code optimization, intermediate code, these concepts, then remember, definition simply means assignment. Okay, so for example, if you have, let's assume x equal to 1, then x equal to 2, x equal to 3, let's assume x equal to 4, then please understand that this is also definition, this is also definition, this is also definition, this is also definition. Means in all these four statements, we are defining x, defining x, defining x, defining x. So please understand, don't confuse this definition word with the C language, with your high level languages. Okay, I am talking about the compiler design terminology. Here you can see every assignment to a variable that will be called defining that variable. Like here you can see in this statement we are defining the variable z and we are using the variable x comma y. Let's consider these examples. Consider this statement as one. Tell me, for this statement s1, what is def of s1 and what is use of s1? Means by this statement s1, which variables are defined? Def of s1 means by this by this statement s1, which variables we are defining. Defining means assignment. We are assigning variable x. And tell me which variables we are reading or which variables we are using. Nothing, empty. So you can see for this statement s1, the use set, that is empty, or I can say that this is basically ref of s1. Tell me about this statement s2, which variables we are defining and which variables we are using. So what is def of s2 and what is use of s2? So you can see by this statement s2, which variables are defined. Def means define means assignment. So you can see variable x is assigned. Okay, and you can see which variables we are reading or which variables we are using, x comma y. These variables we are reading or using. Okay, what about this statement s3? In this statement s3, that is print x, we are printing x. So tell me, is there any variable that we are assigning or we are defining? This statement s3, is it defining, is it assigning any variable? No, nothing. So remember, the def of s3, that will be empty set. What about use of s3? Means by this statement s3, which variables are used? We are using variable x. Okay, very simple. We are printing variable x means we are using the variable x, but we are not defining, we are not assigning any variable. We are not writing anything here. We are reading this variable x. Okay, what about this statement s4? If x less than y, then go to the label L. So tell me here, what is the def of s4? Is there any variable that we are defining? No, no variable we are defining. Yes or no? There is no variable that we are assigning. Definition means assignment. And what about use of s4? Any variable which we are using? Yes, x comma y we are using. Okay, I hope you understood this point. You can consider this screenshot. You can see basically we have two function, ref n. It means by a program point n, or I can say by a program statement n, which variables that statement is referring or it is reading. Reference means read. Okay, and you can see what is def of n. This statement n, it is defining which variables. Definition means assignment. You can see for this statement, the use, which variables are used by this statement, empty. You can see there is no variable that is used by this statement, or I can say there is no variable that is read by this statement. But you can see by this statement this x is assigned. So I can say def of this statement, that will be this variable x is assigned, or I can say this variable x is defined. You can see print x here, this variable x is used, it is not defined. So you can see def of print x, that is empty set, and ref of print x, that is variable x. Ref of this statement x equal to x plus y, here x comma y, these are referenced, or I can say these are used or these are read. And you can see that this variable x, this is defined or this is assigned. Very simple, I hope you understood. So please understand this terminology, this will be very useful, that in the compiler design, whenever I say we are defining a variable, it simply means it is assignment. Definition and assignment, they are same, and use and read and reference, all these things are same. Okay. Now let's study types of analysis. There are two types of analysis. One is data flow analysis, another is control flow analysis. Let me tell you, in the GATE exam syllabus, we only have data flow analysis. We do not have control flow analysis. But just let's see the difference between data flow analysis and control flow analysis. Before we see the difference, let me tell you about the control flow graph. In the previous lectures, we have already seen the control flow graph. In a control flow graph, we have node and we have edges. Yes or no? Just like every graph, we have some nodes and we have edges. The nodes are the basic blocks. You can see each node is a basic block, and these edges, they represent the possible control flow, the possible flow of control, or I can say potential flow of control. So here you can notice that, for example, this is a node. So this is basically a basic block. We already know that in the control flow graph, the nodes, the vertices, these are basically the basic blocks. So this is a basic block, and you can notice this edge. This edge will indicate the possible flow of control. Yes or no? So remember, this edge indicates indicates possible flow of control, possible control flow. Okay. What I mean by possible flow of control, for example, I can say that because of this edge, I can say that from this basic block, the control can go to this basic block. Yes or no? But remember, from this basic block, the control cannot directly go to this basic block. Yes or no? So basically, these edges, they indicate the possible flow of control, how the control is flowing in this control, in this control flow graph. And all the nodes, these are the basic blocks. Okay. So this is the review, or I can say recap from the previous lectures. What is a control flow graph? Control flow graph is basically a graph where every node is a basic block. Okay, you can see this is a graph of basic blocks of a function. I told you that for every function in your program, we make control flow graph. In your program, let's assume there are 10 functions, then there will be 10 control flow graph. Yes or no? For every function in your program, we create a control flow graph. So you can see in a control flow graph, the basic blocks of that function, basically for a function we create the control flow graph. So the basic blocks of that function, these will be the nodes of the control flow graph. And the edges, we have seen that these edges, they indicate the possible flow of control through the program. Okay, very simple. Now I was telling you that there are two type of analysis. One is data flow analysis, another is control flow analysis. Let's see the difference between these two. The name itself is telling you. Control flow analysis means here we discover the flow of control. We do the analysis of flow of control. And in the data flow analysis, we discover the data flow, the flow of data. Let me explain this point. First, let me explain what is control flow analysis. Control flow analysis means we discover the control structure, or I can say the control flow, how the control is flowing in your CFG, in your control flow graph. So let me tell you, for example, from a basic block, can you go to another basic block? Okay. Or I can say that, is there any loop in your graph? Is there any loop? Okay. So remember, is there any basic block which is unreachable from the entry point? Is there any basic block which is unreachable. So remember, all these are basically control flow analysis. I hope you understood. So remember, what is control flow analysis? In the control flow analysis, we understand the order in which statements may execute. Basically, flow of control, we want to understand, we want to discover the flow of control. And you can see in the control flow graph, the edges will tell you about the flow of control. Yes or no? That we already know, that edges in the control flow graph, they will tell you about the possible flow of control. So overall, I want to tell you that any analysis that is related to the edges of the control flow graph, that is your control flow analysis. Okay, so remember this control flow analysis, let me tell you, this control flow analysis, this is basically related to edges. Okay, this is basically related to edges in control flow graph. Now, for example, you can see some examples I've given here. The control flow analysis, this will answer some of these questions. You can see these questions, you can notice, for example, which block will execute next. For example, you can notice here, if you are at this block, then which block will execute next? This block will execute. Who is telling you? This edge is telling you. Yes or no? This is what I'm telling you, that this control flow analysis, this has to do with the analysis of the edges, because in the control flow graph, the edges will tell you the possible flow of control. So please understand that this control flow analysis, this is basically related to the analysis of edges in the control flow graph, related to analysis of edges in the control flow graph. You can see, for example, if you want to answer this question, what block will execute next? For example, is there any loop in your graph, in your control flow graph? Is there any loop? Okay, that also will be told by the edges. Yes or no? For example, is there a path from block A to block B? What are the predecessors of a block? What are the successors of a block? So basically, to answer all these questions, we need to do the control flow analysis. I hope you understood. Okay, so you can see this control flow analysis, it will focus on the structure of the program and the flow of control. Okay, did you understand? Don't worry, this control flow analysis, this is not in the gate syllabus, but did you understand some basic idea of control flow analysis? There are two type of analysis. One is control flow, another is data flow. And in the control flow analysis, we only do the analysis of the control, how the control is flowing in your program. We do not worry about the variables. Okay, we do not worry about the data. We do not worry about these things, like the values of the variables. Okay, so we do not worry about these things. Remember, in the control flow analysis, we only worry about the how the control is flowing. For example, is there a loop? Okay, that also will be told by the edges. Here you can notice there is a loop. Yes or no? Like you can go like this, so there is a loop. Do you agree? So you can notice in this control flow graph there is a loop. So remember, this question will be answered by the control flow analysis. You can see this control flow analysis, it will answer this question: is there any loop present? Which block will execute next? Is there a path from block A to block B? What are the predecessors of a block? What are the successors of a block? All these things, I hope you understood. So you can see control flow analysis, it will discover the information about how control is flowing through the program. Okay, or you can understand in the computer organization terminology, like your program counter. Yes or no? Your program counter, it will keep track of which is the next instruction to execute. The program counter in the computer organization subject, if you did not study, don't worry, but the point is, in the computer organization subject there is something called program counter, and this program counter will keep track of the execution flow. Yes or no? So you can notice that this control flow analysis, this will also discover the information about how the control is moving, how the control is flowing through the program. Now let's see what is data flow analysis. The data flow analysis, the name itself is telling you, we are doing the analysis of the data. We are computing the information about how data means variable, assignments, definitions, values, how this data is flowing through the program. Okay, let me tell you, in our gate syllabus, all the optimizations that we have, all the analysis that we have, these are data flow analysis only. For example, you can see we will study liveness analysis, available expression analysis, constant propagation. All these analysis, these are basically data flow analysis. In all these analysis, we worry about the data, means we worry about the variables. Okay, In the liveness analysis, let me tell you, in this analysis, we focus on which variables are live, which variables are dead at any program point, at any statement, which variables are live, which variables are dead. You can see in the available expression analysis, we focus on which expressions are available at any program point, at any statement, which expressions are available. So you can see that in these analysis, we worry about the data basically. Okay, so you can see we compute the information about how data is flowing through the program. I hope you understood. And you can see in all the analysis that we will study, these are data flow analysis, so it will become more clear what is this data flow analysis. But you can see from this diagram you can understand the data flow analysis has to do with the data. Okay, so you can see in the data flow analysis we discover the information about how data is moving through the program, like variables and their values, how they are moving through the program. Okay, for example, you can see, look at this data, this is a variable. Okay, you can see this variable we are using here. So this type of analysis is called data flow analysis. Okay, in any analysis, if you are thinking about like this variable I'm using here, okay, if you are thinking about these things, then that is definitely data flow analysis. I hope you understood. Now let me tell you, in our gate syllabus we don't have control flow analysis, but one example I want to give you, because for the data flow analysis, these three examples we will see in detailed way. So right now there is no point in discussing the data flow analysis, because when we discuss all these three different analysis, then automatically you will understand what is the data flow analysis. The definition we have already seen, the idea we have already seen. But let me give you one example of control flow analysis, because this control flow analysis, this is not in the gate syllabus. So let's just see one example. Consider this unreachable procedure elimination. This unreachable procedure elimination, this is basically a control flow property. Yes or no? You can notice here that, consider this program. In this program, from the main function, we are not calling the function f. So this function f is unreachable. Remember, there will be a control flow graph for the main function, there will be a control flow graph for the function f. Will there be any edge from this control flow graph of main function to this control flow graph of function f? Tell me, will there be any edge? Will there be any edge? No, there will be no edge. Yes or no? So you can see from this control flow graph to this control flow graph, there will be no edge. So I can say that this function is unreachable, so you can remove it. So please understand that unreachability, that is a control flow property. It is very obvious to understand that some function, is it reachable from the main function? From the main function, is this function reachable? So that is your control flow property. Okay, so remember, unreachability, that is a control flow property. Like you can consider this example here, this is an unreachable procedure. Okay, you can see. So this unreachable procedure we can remove. Okay, this is called unreachable procedure elimination. Okay, so this transformation we can do, because this function f, or I can say this procedure f, this is unreachable from the main function, and the main function is the starting point of the execution. First we execute the main function. Now let me tell you another classification of optimizations. We have already seen that optimizations, or I can say analysis, we can divide into two classes. One is data flow analysis, another is control flow analysis. But let me tell you, there is another classification of the optimizations, or I can say there is another classification of the analysis. That is, we can classify the optimizations in three types. These are the three types: local optimization, global optimization, and interprocedural optimization. Let's understand all of them one by one. This is very easy to understand. This is our control flow graph. In this control flow graph, every node is a basic block, and we already know what is a basic block. Inside a basic block, we have straight flow. Yes or no? You already know that the definition of basic block, you already know that in a basic block, these statements that we have, they will execute in this sequence, in this straight sequence they will execute. Yes or no? So inside this basic block, the incoming flow can come from anywhere. For example, you can see, look at this basic block, let's call it b0. You can see that in this basic block, you can enter from here also, or you can enter from here. You can enter from here, but the point is, once you enter here, once you enter the first instruction, Then you can see from first instruction to the last instruction, these will be executed in this sequence only. Okay, yes or no? So this is the definition of basic block that we already know. You can see inside this basic block, we cannot jump directly to some random instruction. Okay, also from this basic block, we cannot randomly go outside. The point is that all the instructions that you have in this basic block, let's assume this is the basic block, and let's assume this is the first instruction, then this is the second instruction, third instruction, and so on. If these are the instructions, then remember they will execute in this sequence only. Inside a basic block, we have this straight flow, I can say, straight execution flow we have. Now you can see if we are performing some optimization within a single basic block, that is called local optimization. So let me tell you, like this is a basic block, and within a single basic block, if you perform some optimization, that will be called local optimization. Is this point clear? So remember, you can see this is a single basic block. This is a single basic block. And on this single basic block, if you perform some optimization, then that will be called local optimization. So you can see if I perform optimization within a single basic block, then that will be called local optimization. Is that point clear? Let me know. Very easy. Within a single basic block, for example, consider this basic block. Within a single basic block, if you perform some optimization without worrying about the whole control flow graph, if you only think about this single basic block, so any optimization that you perform on a single basic block, within a basic block, if you perform some optimization, then that will be called local optimization. Now let's see what is global optimization. Global optimization means on this control flow graph, on this entire control flow graph, if you perform some optimization, then that will be called global optimization. So you can see this is a control flow graph. This whole graph, this is a control flow graph of a function, of a particular function. Because you already know that for every function we create a control flow graph. In your program, if you have 10 function, then there will be 10 control flow graph. You can notice this is a control flow graph of a particular function in your program, of a particular function in your program. Okay, now let me tell you, on this control flow graph, if you perform some optimization, that will be called global optimization. That optimization will be called global optimization. Is this point clear? Please tell me. Very simple. Remember, if you are performing some optimization within a single basic block only, within a basic block, if you are performing some optimization, that is called local optimization. On the control flow graph of any function, on a single control flow graph, because remember, for every function we create a control flow graph. In your program, if you have 10 function, then there will be 10 control flow graph. So for any particular function, you have a particular control flow graph. Okay, so you can see on a single control flow graph, or I can say on the entire control flow graph, if you perform some optimization, that will be called global optimization. Now let's see what is this inter-procedural optimization. This means on the entire program, if you perform some optimization, that will be called inter-procedural optimization. Means you are going between the procedures. You can notice here we have a main function, we have a function f, function g, function h. I told you that in your program, if you have four function, for example, function main, function f, g, h, these are the total four functions are there. Now you can see there are total four control flow graph. This is the control flow graph, this is the control flow graph, this is the control flow graph, and so on. Now you can see that if you perform some optimization on the entire program, then that will be called inter-procedural optimization. Means you are going between procedures. Your optimization is going between procedures. Okay, remember, if you perform some optimization within a particular function, or I can say if you perform some optimization on the control flow graph of a particular function, that will be called global optimization. But if you go between the procedures, then that optimization will be called inter-procedural optimization. So did you understand the three categories, the three types of optimizations? Local optimization, global optimization, and inter-procedural optimization. Okay, you can see local optimization means within a basic block. Very simple. Within a basic block, you are performing some optimization. That is your local optimization. What is global optimization? That is within a control flow graph. And what is inter-procedural optimization? This means in the entire program, means you can go between the control flow graphs of different procedures. Okay, your optimization moves between the functions, between the procedures. So you can see that is called inter-procedural optimization. I hope you understood. Let me tell you, this global optimization, this is also called intra-procedural. Intra-procedural means within a procedure. Okay, not going among many procedures. Okay, basically within a procedure, if you are performing some optimization, that is called global optimization. This is also called intra. We use the word intra, intra, intra procedure. Okay, so let's see the definition here. You can see the types of optimization. There is local optimization. An optimization is local optimization if it works on just a single basic block. An optimization is global optimization if it works on entire control flow graph. And you can see an optimization is inter-procedural optimization if it works across the control flow graphs of multiple functions. In our gate syllabus, we have these two optimizations: local optimization and global optimization. Okay, and remember, in the local optimization, also in the global optimization, in these optimization also, we have a specific optimization only. Like they cannot ask you some random optimization. Some specific optimizations are there, those we need to study. And in our syllabus, we do not have this inter procedural optimization. Means this optimization which works across the control flow graphs of multiple functions, we do not have to worry about this type of optimization. Very simple. So you can see the classification here, the types of analysis, or I can say the types of optimization. If you are performing some optimization within a basic block, that is called local optimization. You can also call it peephole optimization. What is the meaning of peephole? Let me tell you. Peephole means a small sequence of instructions. A small sequence of instructions. This is the meaning of peephole. A small sequence of instructions. Okay, so remember, if you are performing the optimization within a basic block, then that is called local optimization, or you can call it peephole optimization. And if you are performing optimization between basic blocks, or I can say in a control flow graph, then that is called global optimization, or you can call it intra procedural optimization. For example, liveness analysis, available expression analysis, these analysis that we will study, these are basically intra procedural analysis. These analysis you can perform within the basic block also. You can also perform between the basic block also. Okay, basically on the entire control flow graph, you can perform liveness analysis, also the available expression analysis. Okay, and you can see if you are performing optimization on the whole program, that is called inter procedural optimization. Okay, let me give you one example of inter procedural optimization, which is optimization which works across the functions. Okay, so let me just give you one example, because anyway this is not in the syllabus, we don't have to worry about this inter procedural optimization, but just let me give you one example. You can consider this example. We have a main function, we have a function f, and you can see we are removing this function f because it is unreachable from the main function. So tell me, which analysis goes across the functions? Here you can notice there is a main function, it will have a control flow graph. There is a function f, it will have a control flow graph. So tell me, which type of optimization, which type of analysis goes between the procedures? That is inter procedural analysis, or I can say inter procedural optimization. So you can see that here this procedure is unreachable from the main function, so you can remove it because this is unreachable procedure. So you can notice that unreachable procedure elimination, this is a inter procedural optimization. Okay, so you can see this example, this we have seen that this unreachable procedure elimination. This is example of control flow property, or I can say control flow analysis also. And also this is the example of inter-procedural optimization, inter-procedural analysis. I hope this point is clear. Okay. So just let's see the definition. It is not required for the gate exam, but let's see the definition. What is inter-procedural analysis? Inter-procedural means it will collect the information about the entire program. I told you. Okay. So you can see between procedures, some information you are propagating. So the optimization is going across the procedures. The analysis is going across the procedures. So that is called inter-procedural analysis or inter-procedural optimization. You can see unreachable procedure elimination. If some procedure is unreachable or reachable, so you can see this unreachable procedure elimination. This is example of inter-procedural control flow optimization. Okay, I hope you understood. Now let's see what we have in the GATE syllabus. So far we have seen a lot of concepts, a lot of definitions, a lot of ideas we have seen. But let me tell you, a good thing is that in the GATE syllabus, we don't have all of these things. In the GATE syllabus, you can notice we have local optimization. We will study this. We have data flow analysis. In the data flow analysis also, we only have three analysis. That's it. One is constant propagation, another is liveness analysis, and another is common sub-expression analysis. There is no other analysis, or I can say there is no other optimization in the GATE syllabus. Okay, and what we have in the GATE syllabus, that we will study. So remember, from the GATE syllabus point of view, you do not have to worry about control flow analysis. You do not have to worry about inter-procedural analysis. Okay, in our GATE syllabus, we have local optimization that we will study. Also, this data flow analysis, these three analysis that we will study, these we will study for the entire control flow graph. Okay, means we will study them for a particular basic block also, and we will study them for entire control flow graph also. Means basically these are the global optimizations. Let me tell you, I told you that this liveness analysis, this constant propagation analysis, and this common sub expression analysis, all these three analysis that we have in the syllabus, these are basically global analysis. Okay, so in our syllabus we have local optimization also and global optimization also. Now let's see some simple and standard optimizations. These are not directly mentioned in the GATE syllabus, but they might be asked because these are part of local optimization. Actually, these three are basically local optimizations. Okay, we will see. You will see why they are local optimizations. Let me tell you, these are local optimizations. So you can see in our syllabus we have local optimization, but they did not mention which local optimizations they can ask. So that is the reason I'm going to teach you the standard local optimizations which are given in the standard books like Ullman. Okay, so those we will study because in the GATE exam, if they will ask you some local optimization, then definitely they will ask you from the Ullman book. Okay, so again, I'm telling you that these three, constant propagation, algebraic simplification, and strength reduction, these three, these we will study now as a part of local optimizations. These are local optimizations. Why these are local optimization, that will become clear once you study them. Okay, remember the definition of local optimization. Local optimization means when we perform the optimization within a single basic block. Yes or no? Okay. So let's see all these optimizations one by one. Let's study constant folding. The name itself is telling you what is this optimization. Constant folding. It simply means that at the compile time, if you already know that some expression has all the operands constants. For example, look at this expression. In this expression, all the operands are constant. So at the runtime, you will compute it. Instead of that, what you can do at the compile time, you can replace this with 20. So that on the runtime, when you run the program, you don't have to do this multiplication. So at the compile time, you can replace this with 20. The compiler can do this. This is called constant folding. The name itself is telling you constant folding. We are folding basically. Here you can see this is the expression, and this expression we are folding into 20. The reason is because in this expression all the operands are constant. When all the operands are constant, so we can fold it. This we can fold and we can replace with 20. So this is called constant folding optimization. You can see evaluate expressions at the compile time if they have constant value. If some expression has all the operands constant, then you can evaluate this expression at the compile time, so that you don't have to perform this multiplication at the runtime. Okay, this is called constant folding. You can see here int x equal to 2 plus 3 multiplied by y. You can see, look at this expression 2 plus 3. At the compile time, you can replace this with 5. Okay, so that at the runtime, you don't have to perform this addition. I hope you understood. So you can see this constant folding optimization. What it says that here we evaluate constant expressions at the compile time and replace the constant expression by their values. For example, if you have this expression 2 into 3.14, 3.14, 2 multiplied by 3.14, then you can see it will be replaced by 6.28. This is called constant folding. I hope you understood this. Tell me one thing, is this local optimization, is this global optimization, or is this inter-procedural optimization? Tell me, think about it and tell me. This is local optimization. A single statement only you are optimizing. Yes or no? We are only doing the optimization of a single statement. We are not going between the basic blocks. Within a basic block, for a single statement, we are doing the optimization. So remember this constant folding. This is basically your local optimization. Let's see the next optimization, that is algebraic simplification. You can use the algebraic rules, algebraic theorems, and you can do some simplification at the compile time. Very simple. So you can see at the compile time, we can take advantage of some mathematical theorems, some mathematical simplifications. For example, at the compile time, when the compiler will see a multiplied by 1, then the compiler will replace this with a. Okay, this a multiplied by 1, this will be replaced by a by the compiler, so that at the runtime we don't have to perform this multiplication. Okay, similarly, when the compiler will see a multiplied by 0, then the compiler at the compile time will replace this expression with 0, so that at the runtime we don't have to perform this multiplication. Similarly, you can notice a plus 0 will be replaced by a minus 0 will be replaced by a. You can see b or false. Here this is or. You can see this is or. So what is b or false? When the compiler will see b or false, then the compiler will replace this with b, so that at the runtime we don't have to perform this operation. Next, you can see b and true, that will be replaced by b. Okay. Also, you can see, so basically these are algebraic simplifications we are taking the advantage of some algebraic rules. For example, we can take the advantage of associativity and commutativity. For example, if you have a plus b then plus c, you can also, the compiler, if it is beneficial, the compiler has to decide. If it is beneficial, then the compiler can write it a plus b plus c. Similarly, this a plus b you can replace with b plus a if it is beneficial. The compiler has to decide this. The optimizer, I told you that the optimizer is the very complex program. Okay, yes or no? In your compiler phases, among all the compiler phases, the optimization is the most complex phase. So the optimizer can decide whether this a plus b, if I replace with b plus a, it will be beneficial or not. Okay, will it lead to some other optimization? Maybe when you replace this a plus b with b plus a, then maybe some other optimization you can carry out. Okay, so that will be decided by the optimizer. Okay, so this is called algebraic simplification optimization. Let's see some more examples of this algebraic simplification. You can see, for example, consider this statement a plus 1 bracket then plus 2. You can see at the compile time, the optimizer, what the compiler can do, first compiler can write it a plus 1 plus 2 using the associativity of addition. Addition operation is associative. Then you can see that this 1 plus 2 we can write it this 1 plus 2 we can write it 3. So finally we got a plus 3. Next you can see, look at this, 2 plus a plus 4. Here you can see what the compiler can do, what the optimizer can do. First you can use the commutative property, 2 plus a, you will write it a plus 2. Then you will use the associative property, so you will write it a plus bracket 2 plus 4, and this 2 plus 4 you can write by 6. So finally you got a plus 6. So these are algebraic simplifications. We are using the algebraic rules like commutative property, associative property, some identities, algebraic identities. Okay, these we are using. For example, x plus 0, 0 plus x, you can replace with x. X minus 0, you can replace with x. X into 1, 1 into x, you can replace with x. X divided by 1, that you can replace with x. Okay, so you can see these this type of simple optimizations you can carry out. Tell me, these are local optimizations or global optimization or inter-procedural? These are simple local optimizations, yes or no? These optimizations you carry out within a single basic block. Basically, for a single statement, you perform these optimizations. So definitely these are local optimizations. Okay. Let's see the next optimization, that is strength reduction. The name itself is telling you that strength we are reducing. It's very simple. To do some work, if you need a needle, if needle is enough, then why do you need a sword? Yes or no? In Hindi I can say like, अगर needle से काम चल रहा है तो आपको तलवार की क्या जरूरत है? Similar to that. So remember, strength reduction. What it means? It means that we replace the expensive operation with a cheaper operation. Tell me, addition multiplication, which is expensive? Addition or multiplication, which operation is expensive operation? Or I can say which is harder operation? So that is multiplication. Yes or no? So remember, when the compiler will see x square, then the compiler will replace this with x plus x, so that the compiler does not have to do this exponentiation. Okay. So you can see the compiler will sorry, x into x. When the compiler will see x square, the compiler will replace this with x into x, x multiplied by x, so that the compiler does not have to do this exponentiation, because instead of this exponentiation, multiplication is cheap operation. Okay. Similarly, you can see 2 multiplied by x. Instead of doing this, the compiler will replace this with x plus x. Okay. Similarly, x by 2, the compiler can replace this division by multiplication. So remember, this expensive operation we are replacing with cheaper operation. Okay. For example, multiplication with 4, you can replace with left shift. Yes or no? Left shift with 2 positions. Left shift by 2 positions. Okay, so you can see that if you multiply by 4, instead of that, what you can do, you can just left shift by 2 position. Okay, do you know this concept? In the computer organization we study, in the digital logic also we study. For example, let me just explain this point, that on one side let me write a binary number. Okay, and on another side I will write this binary b, and on another side I will write 2 multiplied by b. Okay, so you can notice, for example, if I have 101, this means 5. Yes or no? This binary number, you already know this means 5. Okay, so tell me, what is 2 multiplied by b? That will be 10. Okay, and if you find the binary of 10, that will be 1010. Let me tell you a easy way. A easy way is very simple, that you can left shift this. Okay, you can see if you want to multiply this with 2, then what you can do, this you can left shift. Okay, just do the left shift, means 101 you shift, on the left you shift it, and here you just put a 0. Okay, is this clear? So remember what we have done, we have done left shift one time, one time left shift. So when you do left shift one time, that is like multiplying by 2. Okay, and remember, if I left shift by 2 positions, okay, let me shift it on left by 2 positions, so 2 position I will put 0 0. Okay, now you can notice this means we are multiplying by 4. Okay, and if I left shift by 3 position, that is like multiplication by 8. Yes or no? Here you can notice this will be multiplication by 4. And you can notice that if I want to multiply by 8, then what I can do, I can left shift 3 positions like this. I hope you understood. Okay, so very easy point that when you want to multiply by 4, then the compiler, what it can do, it can replace this multiplication operation by left shift operation, because left shift operation is very cheap and multiplication is expensive operation. So I hope you understood the concept of strength reduction. All these decisions need to be taken by the compiler, by the optimizer. Optimizer is a very complex program and very smart program, I can say. Okay, so basically we are the programmer. Okay, the human mind, that is very, I can say, powerful. When they are writing the code for the optimizer, they will they will write all these things, remember. Okay, so remember, this decision will be taken by the compiler or by the optimizer. So basically this type of optimizations can be done, that we can replace a expensive operation by a cheaper operation, so that it will take less amount of time when at the runtime. Okay, when you run the program, it will take less amount of time. I hope you understood all these points. So you can see strength reduction. What it means? This is an optimization which will replace expensive operation. For example, multiplication, division, these are expensive operation. You can replace them by addition, subtraction if possible. Now let's see the next optimization, that is chord motion optimization. This is also called loop invariant chord motion optimization. Let's understand what is this chord motion optimization. The one example we have already seen in the beginning of this lecture. We have already seen the example of chord motion optimization. Let's see the same example again. You can consider this program. This program, in this code, you can notice that this expression k multiplied by 2, this expression is not changing when this while loop is running. You can notice, because in this while loop, when this loop is running, the value of k is not changing, the variable k is unchanged. So I can say this result of this expression, that is also unchanged. But you can see, if this loop is running 1000 times, then 1000 times you are performing the multiplication unnecessarily. 1000 times you are doing this multiplication. So what is the better thing? The better thing is that this k multiplied by 2, this expression, you only compute one time. Basically you shift it outside this loop. Okay, you put it outside this loop, you compute it only one time, and then you use it in this loop. Because anyway, when this loop is running 1000 times, anyway, this result of this expression is unchanged. So unnecessarily 1000 times you will do the multiplication. So you can save a lot of time if you put it outside the loop. Okay, so this is called chord motion. Okay, and remember, when can we do this chord motion? Chord motion means, from this loop we are moving some code whose result is unchanged by this loop. When this loop is running, okay, any number of iterations you run this loop, the result of some expression is unchanged, then that expression you can move out of the loop, so that when this loop is running, you don't have to unnecessarily every time, in every iteration, you don't have to compute that expression. Okay, so just compute that expression one time outside the loop, and then you use the result in the loop. Okay, very simple. Remember, this is not chord motion. For example, you can notice, in this program, when this loop is running, look at this expression k multiplied by 2. Can I take it outside the loop? No, I cannot do that, because you can see, in this loop, when this loop is running, the variable k is changing. Yes or no? The variable k is actually changing. So I cannot take this expression out of the loop, because you can notice the result of this expression is changing when this loop is running. The result of this expression is also changing. Okay, so remember, from this program, if you convert this program to this program, that will be wrong. That is a wrong transformation. So you can see this transformation is not correct. Okay, so let's see the definition of chord motion, or I can say loop invariant chord motion. Why we call it loop invariant chord motion? Because we will move only that chord which is unchanged by the loop. Okay, loop invariant means the code which is not changed by the loop, that code we can move outside the loop. Okay, so you can see, some expression inside the loop are redundant, in the sense that they get recomputed on every iteration, even though their value never changes within the loop. Loop invariant code motion, it will recognize this type of redundant computations, and it will move this type of expressions outside the loop body so that they are only computed once. Okay, so you can see the definition of code motion. Code motion optimization, it means to move a statement within a loop to outside the loop if possible. Okay, and remember, we can only move that statement which is a loop invariant, which is not changed by the loop. When loop is running, then that expression is, the result of that expression is not changing. So you can see here, find code in a loop body that will produce the same value in every iteration. Okay, this code you can move out of the loop so that it is not computed over and over again. Okay, because it will be a waste of computation resources if you do that. So instead, what you can do, you can just move it out of the loop so that you only compute it one time. Very simple. So you can see. So you can see code motion will move code outside of a loop if possible. Consider this example. Can we do any code motion here? Tell me, can we make it better? This program, can we make it better? Let's assume this while loop is running 1,000 times. Then 1,000 times this addition you will perform. And let me tell you, this is unnecessarily you are performing 1,000 times, because you can see when this loop is running, variable y is also not changing, variable z is also not changing. So you can see the result of this expression is unchanged. Yes or no? So I can say that this is basically loop invariant code. Yes or no? This is loop invariant code. And when this loop is running 1,000 times, then also the result of this expression is unchanged. So what you can do, you can just take it outside, just compute it one time, store the value in some variable t, and then you use this variable t in the loop. X less than t. Okay, x is equal to x minus y. That's it. Okay, so I hope you understood this point. Now you can notice that when this loop is running 1,000 times, then we are not performing this addition 1,000 times. We are only performing this addition one time. That's it. Okay, so this is called code motion, or you can call it loop invariant code motion. So you can read everything that we have seen that is written here. You can read this paragraph. You can consider this example also. Let's assume you have while I is less than equal to limit minus 2. And let's assume when this loop is running, let's assume this limit is unchanged. Okay, you can see, let's assume that this loop is not changing the variable limit. Okay, so you can see that if this while loop is running 1,000 times, unnecessarily 1,000 times you are doing this subtraction. But if you notice, the result of this expression is unchanged. Whatever iteration you do, the result of this expression is unchanged. So what you can do, so the better thing is code motion. So you can just take it outside this expression limit minus 2, you can take it outside, and then the result you can use in the while loop. Okay, so this is called code motion. I hope you understood. You can consider another example. Consider this program. In this program, let's assume the string length is unchanged. If string length is unchanged by this loop, when this loop is running, if the string length is unchanged, then unnecessarily, let's assume this loop is running 1,000 times, then 1,000 times you are calling this function. This function you are calling 1,000 times. So what is better way? The better way is that if this string length is unchanged by this loop, then what you can do, you can just call this function one time, and you can store in some variable t. Okay, you can just call this function one time, and you can store in some variable t, and then you can just use this t, so that when this loop is running 1,000 times, then unnecessarily 1,000 times you are not calling this function. Okay, yes or no? So I hope you understood the point. This is called code motion. Let's solve this question. This is gate 2014 question. Let's solve it. What will be the answer? Which of the following is false statement? A basic block is a sequence of instructions where the control enters the sequence at the beginning and the control will exit at the end. Is this correct definition of basic block? Yes, this is the correct definition of basic block. Yes or no? We already know the basic block definition. In a basic block, the control will enter at the beginning and the control will exit at the end. Basically, a basic block is a sequence of instructions which will always execute as a unit, which will always execute together. Okay, and in this basic block, the first instruction is called the leader. Okay, so you can see if these are the instructions in the basic block, then remember in this basic block, if you have these four instructions, then they will always execute in this sequence. First, this instruction will execute, then this instruction will execute, then this, then this. Okay, you can notice that the control will enter at the beginning. The control can enter from many sides. Okay, and the control will exit at the end. Okay, but the point is that the control will not exit from the middle. You cannot do this. Okay, the control will not exit from the middle. Similarly, the control will not enter in the middle. Okay, the control will enter in the beginning only and the control will exit in the end only. And these instructions in this basic block, they will execute as a unit. They will all execute together in this sequence. That's it. Okay, so you can see this is the correct statement. What about statement B? Available expression analysis can be used for common sub-expression elimination. This we have already seen. This is true. Statement B, that is also true. Okay, I told you that this available expression analysis, this we do to perform common sub-expression elimination, also copy propagation. Okay, this I told you that for common sub-expression elimination and also for the copy propagation, for these optimizations, we perform the available expression analysis. So statement B, that is also true. Statement C, live variable analysis, that is liveness analysis. So live variable analysis can be used for dead code elimination. Yes, this statement is also true. This live variable analysis we do for dead code elimination, also for register allocation. Okay, so there are two applications of live variable analysis. These two applications are dead code elimination and register allocation. The question is asking false statement, but statement A, B, C, these are actually true statement. Let's see statement D. X equal to 4 into 5. We are replacing this. This symbol means replace. We are replacing this by x equal to 20. Tell me, this is example of which optimization? You can notice x equal to 4 into 5. This statement we are replacing by x equal to 20. This is the example of constant folding. Yes or no? This optimization is called constant folding. I told you the definition of constant folding. Constant folding optimization. In the constant folding, what we do? If some expression has all the operands constant, like here you can notice this expression has all the operands constant. All the operands are constant in this expression. So at the compile time, you can replace, at the compile time, the compiler can replace this 4 into 5 by 20. Basically, we are doing the constant folding because this expression is constant. So at the compile time, this expression we can replace with the value. Okay, so that at the runtime, we don't have to perform this multiplication. So at the compile time, we can do this. And this optimization is called constant folding optimization. So the statement D is saying that this is example of common sub-expression elimination. No, this is false. This is example of constant folding optimization. Okay, I hope you understood. So for this question, the answer will be option D. Very simple question. I hope you understood. Now let's study the next topic, and this is a very important topic, that is liveness analysis. It is also called live variable analysis. Both are the same thing. And also dead code elimination. So this is the topic that we need to study. Let me tell you, this dead code elimination, this is basically the transformation, and this liveness analysis, this is the analysis. I told you that in most of the optimizations, we have two things. First, we do the analysis, then based on that analysis, we perform the optimization. So you can notice this dead code elimination, this is the transformation, or I can say this is the optimization. This dead code elimination, this is the actual transformation, or I can say this is the actual optimization that we need to do. But to perform this optimization, to perform the elimination of dead code, what we need to do? We need to do the liveness analysis. This analysis we need to do. And let me tell you, once we do the live variable analysis, then we can perform this optimization, dead code elimination. We can also perform register allocation optimization. Okay, so remember, from this analysis, we can perform multiple optimizations. So you can see this live variable analysis. This is the analysis that we need to perform. Then after this analysis, we need to perform the dead code elimination. Okay. First, let's understand what is dead code. Let's see the definition and let's understand with the help of examples. Dead code, or I can say the better word will be dead assignment. Okay, this is the better word actually. Instead of using the word dead code, you can understand that it is basically dead assignment. Now, what is the meaning of dead assignment or dead code? You can read this definition. An assignment to a variable v. I am talking about assignment to a variable v. Assignment means definition. I told you definition means assignment. So, an assignment to a variable v is called dead if the value of that assignment is never read anywhere. Read means use. Yes or no? These small points we already know that read means use. Okay, this read word, this means use, or I can say reference. And this assignment, this means definition. Assignment is definition, definition is assignment. Okay, so this means def. Okay, so let's see the definition here. An assignment to a variable is called dead if the value of that assignment is never read anywhere. If the value of that assignment is never used anywhere. Okay, so if some assignment is dead, then we can eliminate it from our code, from our intermediate representation. From that, we can eliminate the dead assignment. Okay, so now let's understand with the help of example. Consider this example. Let's assume this is a program. You can see here we have four assignments. Remember, here we are assigning x, here also we are assigning x, and assignment means definition. So you can see here we are defining x, here we are defining x. In all these four statements we are assigning x, or I can say we are defining x. Okay, so you just tell me a simple point. Use your common sense and tell me, here we are assigning x equal to 1. This assignment are we going to use anywhere? Just tell me, this assignment are we going to use anywhere in the whole program? Maybe this is just for instructions, maybe some other instructions are also there in the program. Okay, there can be many other basic blocks, there can be many other instructions also can be there, but the point is these are the consecutive instructions. Now you tell me, this assignment will we ever use anywhere? No, we are not going to use, because you can see in the next line we are assigning x to. Okay, so you can notice this is useless. This statement, do you agree that this is a useless statement? This is a useless assignment. Why? What is the reason? Because on the next line we are assigning x equal to 2. So this assignment is never used anywhere. You can guarantee that this assignment will never be used anywhere, because on the next line we are assigning x 2. Okay, yes or no? So you can see this will never be used, or this will never be read anywhere, this assignment. Okay, so that is the reason I can say this is a dead assignment. Okay, so please understand this. I can say that this is a dead assignment, or I can say this is dead code, or I can say this is dead assignment. So even if you remove it, it does not matter. You can remove it. It is a useless assignment. Okay, what about the next statement? What about this? This is also useless assignment, because on the next line you are assigning x equal to 3. So this assignment is also never used. Next, you can notice this x equal to 3. This assignment is also never used. Yes or no? So you can notice that these assignments are never used. Okay, but what about the last one? What about this last one? This may be used somewhere. Yes or no? Maybe this assignment will be used somewhere. Okay, I don't know. But I can guarantee for these three assignment that these three assignment will never be read anywhere. They will never be used anywhere. They are useless assignments. They will never be used anywhere. Okay, yes or no? Maybe this assignment might be somewhere used. Maybe somewhere used. Okay, may be used somewhere. This may be used somewhere, but for the remaining three assignment, I can guarantee that they will never be used anywhere. They will never be read anywhere. So that is the reason I can say these three assignments you can remove. Even if you remove from the program these three, then also it does not matter. Do you agree? Okay, so remember these can be eliminated. Okay, is this point clear? Can eliminate. You can delete these three statements from your program. So you can see dead code elimination will remove statements that are no longer needed. Okay, these three statements are no longer needed because of this statement, because of this x assigning for, because of this. These assignments will never be read anywhere. They will never be used anywhere. So these are useless statements, useless assignments. So you can delete them. Let's consider this example, slightly more complicated example. In this example, you tell me, is there any assignment which is dead? Is there any assignment which will never be read anywhere, which will never be used anywhere? Let's consider this assignment. Tell me, just look at one by one. Okay, let's go one by one. Tell me, this assignment, will it ever be used anywhere? You can see these are simple instructions. These are not jump instructions. These are simple arithmetic instructions. So they will always execute in this sequence. There is a guarantee. Okay, this will be the execution sequence that you already know, because these are simple arithmetic instructions. So after this instruction this will execute, after this instruction this will execute, and so on. Okay, these instructions will execute in this sequence. Now you tell me, look at this assignment. Here we are assigning x. Okay, you can see here we are assigning x. Okay, tell me, in this statement, what is the def of this statement? For this statement 1, what is the def of 1? What is the use of 1? Let me know. Means in this statement 1, which variables are defined, and in this statement 1, which variables are used? In this statement 1, you can see that variable x is defined and variable y is used. Yes or no? Use means read, I told you, and define means assignment. You can see we are assigning variable x. Okay, so you tell me, this assignment, will it ever be used? Means I am asking, this particular assignment, will it ever be read anywhere? Will it ever be used anywhere? You can see here we are not using. What about the next? Here you can notice we are again assigning to x. So actually you are using x here. Here we are using x. Here we are using means reading. Here we are reading x. Okay. But the point is, here this x we are reading. Do you agree with me? Tell me. This x actually we are reading. Basically, this assignment is used. This assignment is used. But actually, this assignment is never used. Agree? The first assignment, look at the first assignment. We are assigning some value y plus 1 to x. But this assignment will never be read anywhere, because you can see here we are not reading x. Here you can see we are assigning to x. So in the future instructions, this assignment will be used, not this assignment. Okay. Is this point clear? Please tell me. So remember, I can say this assignment is not used anywhere. I hope you understood this point. So remember, I can say that here I can say this assignment is not used anywhere. Is not used anywhere. Okay. Very simple. I hope you understood. What about the next statement? So remember, this assignment is dead. I can say this statement is also dead. You can remove this statement. Okay. What about the next assignment? Only focus on this assignment. Is this assignment ever used? In this second statement, some value we are assigning to the variable y. So variable y we are assigning. Will it ever be read anywhere? Will it ever be used? Yes, we are using here. Okay, you can see in this statement we are using y comma z and we are defining x. You can see in this statement 3 we are using y comma z. Okay, and you can see that in this statement 3 we are defining x. Okay, so you can see that definitely this assignment is not dead, because this assignment actually you are using here. Okay, what about the next assignment? What about this third assignment? This also I'm using here. Okay, yes or no? Here I'm using. What about the next assignment? What about this z equal to 1? In this fourth in this fourth statement, this one I am assigning to z. This assignment, will it ever be used anywhere? No, it will never be used anywhere, because in the next statement you are assigning x to z. You are assigning to z again. So please understand that this will never be used anywhere. Yes or no? Okay, look at this. This assignment will never be used. Never used assignment. This is never used assignment. This assignment we are never going to use, because please understand in the next statement again we are assigning to z. So in the future statement, if you are using z, then this z you will use. Yes or no? In the future, if you are using z, then this is the z that you will use. Definitely I can say that this assignment you will never use. So this also I can remove. So remember, this first and this fourth statement, these are dead code, so you can remove them, first and fourth. I hope you understood. So you can see we need to know whether the values assigned to x at the statement 1 is never used. Okay, yes or no? And this we have already seen. Please understand one more thing, that we are looking the use of assignment. Please understand that basically you have some assignment, something like this, that here this x is assigned. Here I can say this x is assigned. Okay, and remember, we are checking whether this particular assignment will be used somewhere. Okay, see, this is called def. Assignment means definition. So this is called def. And basically we are checking that this particular assignment, are we using somewhere? Are we using somewhere? We are checking use. Okay, use means read. Read means reference. So please understand, this is what we are checking, that is this definition used somewhere? Def use. This def use we are checking. Okay. But remember, after this definition, let's assume if we have another definition x, another definition of x means another assignment of x, then definitely this definition we are not using here. This definition we are using here. Yes or no? Is this point clear? So please understand, this is what we are checking, def use. Okay, def use. This def use we are checking. Do we have this def use? Okay, if you have this def use, means for this assignment, for this definition, if there is somewhere use, okay, in this situation we will say that this assignment is not dead. Okay, if this is there, I can say if it is possible, if it is possible, then I can say, then this particular assignment, let's call it, let's call it statement 1. Okay, statement n, let's call it statement n. So remember, then assignment at statement n is not dead. Assignment at statement n is not dead. Okay, not dead means alive. Very simple. Not dead, that will be alive. Not dead means alive. Live. I hope you understood. Now let's see this example. This is slightly more complicated than the previous example. Here you can see we have a if statement also. So tell me, let's check one by one. You tell me this assignment, is this dead assignment or not? Tell me. Look at this assignment. here we are assigning x. Okay, so just focus on this x. I am asking, this assignment, is it used anywhere? This particular assignment, are you going to use anywhere? Like, is it possible that this assignment can be used somewhere? Is it possible? You can notice, yes, this is possible. Notice here we are defining x, here also we are defining x, but here we are using x. Okay, before we solve this question, first let me tell you that here what we are defining and what we are using. Tell me what we are defining. We are defining x. And tell me what we are using. What we are using, we are using y. Okay, so tell me for every statement. For this statement, what we are defining, you can see what we are defining. We are defining y. And what we are using, we are using z. Okay, what about this statement? Tell me about this statement. What we are defining, we are defining x. And what we are using, we are using yz. Okay, what about this statement? What we are defining z. What we are using, nothing, no variable we are using, empty. Okay, what about this statement? What we are defining z. And what we are using x. Okay, clear? Very simple. So I hope you understood. Please understand one more thing. Here we are not using x. Okay, please, this is important point to understand that here we are not using x in this statement. We are not using x because you use means read. Okay, remember, use means read. Okay, and define means assignment. Okay, so please understand that here in this statement we are not using x. Okay, and one more thing, here we are not defining x. You can see here we are not defining x, not assigning x, or I can say not defining x. Okay, clear? Now let's solve this question. So tell me, look at this statement, or I can say look at this assignment. Is this assignment possible to be used somewhere? Or can I say that this assignment will never be used anywhere? You can notice here we are using x. So is this assignment we are using here? Is it possible that this assignment we can use here? Let's see. Yes, it is possible. For example, if this d is 0, if this d is false, then what will happen? Then this assignment, and if this d is false, then this will never execute. Okay, yes or no? See, if I am saying if d is false, assume if d is false, d might be false, d might be true, I don't know. At the runtime we will get to know, but at the compile time I don't know whether d is true or d is false. Maybe at the runtime, maybe this d is false. If this d is false, then this will never be executed. Okay, yes or no? If this d is false, then this will not executed. It will not be executed. And if this will not be executed, then what will happen? Then here the x that we are using, that will be this assignment. Yes or no? So you can see that this def, this is the definition, or I can say this is the assignment. So this is the def and this is the use. Okay, and you can see if d is false, then this def use we will get. Okay, yes or no? This def use we will get. So very simple, this def use we will get if d is false. I hope you understood. So remember, I cannot say that this assignment will never be used. It might be used, yes or no? This assignment may be used if d is false. So definitely this is not dead. Okay, is this clear? So definitely I can say that because this def use possibility is there. Okay, because of this possibility, I can say because of this, I can say that. So I can say that this x equal to y plus 1, this statement is not dead. Is not dead. Okay, you cannot remove it. It is not dead. It is live. It is alive. Okay. Now, what about the next statement? Tell me, this variable, this assignment y, this assignment y, is it possible it can be used somewhere? Or can I say it will never be used anywhere? Yes, it can be used. If d is true, then you can see this will be used here. Yes or no? If d is true. Okay, do you agree with me? You can notice if d true at the runtime, if d is true, then you can easily notice that this assignment, this is the def and this is the use. Okay, this is the def and this is the use. So you can see this possibility is there. Def use possibility is there for this assignment. For this assignment. Okay, so definitely this assignment is also not dead. So the question is asking, is this a dead code? The answer is no. Okay. Second, this statement is also not a dead code. What about the next statement? What about this? X equal to y plus z. What about this one? Means, what about this assignment? Is this assignment dead or alive? Let me know. You can see if D is true, then this statement will be executed. And after that, this X will be used here. Yes or no? You can notice. So this def use situation is there. Okay. Do you agree with me? You can notice if D is true, then this def use situation will be there. If D is true. So definitely I can say that this assignment is also not dead. What about the next? You can see this z equal to 1. Yes, this is definitely dead. Yes or no? This assignment is definitely dead because in the next line, we are assigning x to z. Okay, yes or no? So you can see that this assignment will never be used anywhere. So the question is asking, is z equal to 1 dead code? The answer is yes. This is still a dead code because this assignment z equal to 1, this assignment will never be used anywhere because on the next line, we are assigning some different value to z. So in future, if z will be used, then this z will be used, means this assignment will be used, but this assignment will never be used. I hope you understood this example. So you can see that this statement is not dead because on some execution, what is that execution? When d is 0, when d is false. So you can see on some execution, when d is false, then you can see this definition will be used here. So definitely this statement is, you can see this statement is not a dead code. Let's consider more complicated example. Now we have a while loop here. Now let's see. The question is asking this x equal to y plus 1. Is this a dead code? This z equal to 1. Is this a dead code? Let's see. In this program, is there any dead code or not? So first you tell me about this assignment. Is this assignment a dead code or not? Is it possible that this assignment can be used in some execution? Is there a possibility of def use, def use for this assignment? Tell me. You can see, first of all, you notice where x is used. You can see here x is defined, here x is defined. This is the only place where x is used. Okay. Now, is it possible that from this assignment I can go to this use? But remember, I cannot go through this assignment because once I execute this assignment, then this x will be used here. Okay, this assignment will be used here. So I am asking that, is it possible that from this assignment you can go to this use? Is it possible? Let's see. If this while loop is running, let's assume. Okay, this statement will execute, then this statement will execute. Let's assume that d is false. If d is false, then this statement will not execute. Okay, so you can see this does not execute if d is false. Then this will execute and then loop will run again. And let's assume now the condition becomes false. Now, if the condition becomes false, this did not get executed, and now the condition has become false. Now we will go out of the loop, and now here x will be used, and that will be this x. Yes or no? So notice one thing that this def, this is the definition, this is def, and this is use. So I got this def use chain. Basically, this def use I got. Okay, how did I get? I got that. Okay, just assume. because at the runtime this might happen. Assume one iteration only, assume only one iteration of loop, of while loop. Okay, assume only one iteration of while loop you assume. In the second iteration, let's assume this condition becomes false, and assume d false. Okay, so because d is false, if d is false, let's assume at the runtime, because I don't know whether d will be true or false, yes or no, I don't know. At the runtime this will be decided, at the compile time I don't know. So you can see, if d is false and if this loop run only one time, then this statement will not be executed. And if this statement is not executed, then this definition will be used here. So the question is asking, is this a dead code? The answer is no. Okay, yes or no? Because there is a possibility of def use. We are just looking at the possibility of def use. I cannot say that this statement, or I can say this assignment will never be used. I cannot say that. Yes or no? I cannot guarantee that this assignment will never be used, because I've already given you a situation where this assignment may be used at the runtime. Okay, so definitely this is not a dead code. What about the next statement? What do you think about this statement? This assignment. Look at this assignment. Yes, it might be used if d is true. Okay, if this loop runs, let's assume one time, and if d is true, then definitely this assignment will be used here. Okay, very simple. What about the next? What about this statement? Is this dead? This statement, you can see, let's assume loop is running. First, this statement will execute. Then let's assume d is true. If d is true, then this statement will execute. And now let's assume this condition becomes false. Then we will go outside the loop. So this will be used. So definitely I can say that yes, this def use is possible. Okay, this def use is also possible. What about the next? This z equal to 1. You tell me about this z equal to 1. Tell me about this z equal to 1 means this assignment. Is it possible that this assignment can be used somewhere? Can I get a def use situation for this assignment? Here you can notice this is def. Here we are defining z. We are assigning z. Assignment means definition. So here we are defining z. Can I get a def use situation for this assignment? Let me know. You can see, let's assume this loop is running. First, this statement will run, then this statement will run. Let's assume d is false, then this statement will not run. Then this statement will run. So this z will be assigned. Now let's assume another loop iteration is there. Let's assume condition again becomes true. Now you can see this z will be used here. Okay, do you agree with me? See, this z will be used here. Isn't it interesting? You can see this is the use of z. So please understand, yes, this def use situation is possible. If this loop is running two times, then definitely this def use situation will be there. Okay, so I can say, is this a dead code? The answer is no. What about the last one? For the last statement, you cannot say, because remember, maybe this is just a part of the program. There can be future program also. Maybe in the future instructions, maybe this Z you are using. Okay, yes or no? So remember, for the last instruction, you cannot say anything, because maybe this instruction, or I can say this assignment, maybe this assignment Z might be used somewhere. I don't know. Okay, so remember, this is the last instruction. For this last instruction, we cannot say anything. It should be given in the question whether it is dead or alive. Okay, so remember, for this last instruction, we cannot say anything. For the last instruction, we can't say. We can't say. Okay, very simple. I hope you understood all these points. So, did you understand the definition? Tell me. So, you can see this example we have already seen. I told you that this assignment might be used here. If this loop is running two times, then this assignment will be used here. Okay, so for this assignment, there is a def use. You can see. So, definitely this assignment is not dead. So, this is what we have seen. So I hope you understood the definition of dead assignment. So remember, an assignment to a variable is called dead if the value of that assignment is never read anywhere. Okay. In that situation, that assignment will be called dead. And this type of dead assignment you can remove from the intermediate representation. So you can see dead code elimination will remove dead assignment from the IR. Okay. Very simple. In the next lecture, we will continue the discussion of liveness analysis, also the dead code elimination. In this lecture, we have seen the idea of dead code elimination, like what is the dead code, what is the definition of dead code, some examples we have seen. But in the next lecture, we will study the liveness analysis, and from this analysis, we will perform the dead code elimination. Also, we will solve the gate PYQs and many other practice questions. Okay. Thank you, everyone. I hope you understood everything that we have seen in this lecture. Okay. Thank you.